Thanks a lot for the introduction, and first of all, thanks a lot to you and the rest of the organizers for the kind invitation to this workshop. Very interesting, I must say. And I will talk about some results, selection of course, of boundary and surface critical phenomena which have happened in the past few years. Now, boundary critical phenomena is maybe a mature subject that has been investigated a lot, at least in StatMech and also in condensed matter. But in the last years, it received a quite renewed interest. And I think one can identify maybe three intersecting lines of advancements that have fueled this renewed interest. One is the advancement in CFT, field theories, and we have heard a lot of interesting talks over the week. New results, also new methods like the phase sphere, the conformal bootstrap, that the focus of this workshop. Maybe more on a condensed matter side of the story, there has been some advancement and also some surprises in studying the physics of quantum magnets in the presence of boundaries, and also even of classical magnets, where there has been some unexpected advancement in the last years. And also another rapidly advancing topic, which I will not talk much, is that of the interplay of boundaries, boundary modes, and topological phases of matter. Now, in my outline, my talk, I've divided more or less in three topics. I will talk about first some surprises, new results that we have found in the most simple models of critical phenomena, the ON models. But in the presence of boundaries and defects, there a few aspects were not fully understood until recently. Then we'll talk about a little bit, as a small intermezzo, physics of some dimerized quantum spin models, which also have attracted some surprises, have shown some surprises in the last years, and also have attracted quite some work in this sense. This is a bit of an unfinished story that not everything is really fully understood, I think. And lastly, I will talk about some more recent work where we have computed systematically the operator product expansion coefficient for various Ising universality class in the presence of a surface. So let's get started by the first part of the talk. Some of you may have heard already a part of it, so I will try to not bore you too much. The ON model, that's the most ever studied model in critical phenomena. For many values of n is physically interesting. For n equal 1 is the Ising model. If you put this in the presence of a surface, generally, without losing generality, you can study the phase diagram as a function of some bulk coupling constant and some boundary coupling constant, and the phase diagram is this one here. So when the bulk is capped, you can imagine on the paper to integrate out the bulk, and you basically get a 2D surface that undergoes the usual 2D transitions. The interesting part is nothing particularly interesting is happening here. The interesting part is when the bulk is critical, because then you cannot really separate the surface from the rest, and you have three different boundary universality classes, and stable one and ordinary, and the extraordinary, which actually is an ordered phase, and then a special in between, which has a relevant direction. Now, the ordinary has been studied a lot. The special also has been studied. Our critical exponents are available. Basically, at the special, you have of interest in critical phenomena, you have one exponent for the boundary fields and one exponent for the leading scaling fields here. Things are maybe more interesting when you take the O2 models, because for the O2 model, qualitatively, the phase diagram is similar, except that the transition into D is a special one, the Berezinski-Kostelis-Taules transition. And for a long time, it was not clear what happens here on the extraordinary line. You go from a quasi-long-range order phase to an order phase. And the question whether this jump is first or second order, or whether it's really magnetized here already on the extraordinary log, on the extraordinary phase or not. This was not easy to understand from Monte Carlo simulations. And we now know why, because there is a new phase. It's called the extraordinary log phase, which is almost ordered. That's why the two-point function decays very slowly, and that's why it was hard to get. For the ordinary, instead, we have this has been studied much more in detail. We also have I also have some more recent calculation of the critical exponents on the ordinary line. even more interesting is the case of Heisenberg model, because for a long time it was thought that there should be just the ordinary phase. Why? Because in a sense, this surface transition for n equals 3 has been shifted to infinity. So then the idea was, well, maybe also the transition point especially has been set to infinity. Actually, this is not the case. So early simulations were compatible with the idea that you just have a single phase here, maybe a slow crossover to the ordinary phase. Later simulation already pointed out to maybe the existence of some sort of transition here, which they call it KT-like. We now know that this transition is actually a standard one. However, it has one exponent, the relevant exponent, which is very close to being irrelevant. So that's why it was hard to single out the special transition. And again, we flow after the special transition to the extraordinary log phase. That's a phase which was first predicted by Max a few years ago, and where the two-point function decays as a power of a logarithm, so extremely slowly, but it's not symmetry broken. And the same physics, the same phase diagram with an extraordinary log phase separating an ordinary and a special universality class persists for ON model for n up to some threshold. We know that there is a threshold like this because for n equal 2 is for sure we have the extraordinary log phase. For a large n, we know from the RG flow that it cannot exist. And so somewhere in between there must be a change of this phase diagram. And this NC now is probably close to 5. That's estimate we have at the moment. A similar picture also happens when you have instead a 2D plane, a defect, immersed in a 3D bulk. Then also generalization of the field theory argument for the extraordinary phase presented by Abhikrishnan and Max show that also in this case you have an extraordinary log phase for n equal 2 and also for any n larger than 2. Then you don't have the surface or defect transition, but the extraordinary log phase persists for any value of n.
Just can you remind us, so if you have a 2D plane and you have Ising on both sides, is it different critical exponents than or boundary critical exponents, so plane defect, on the defect, the operators?
No, because on one side you can imagine to disconnect the two. When the coupling are very, very small and on the planes, you basically disconnect and you have two surfaces, and that's the ordinary. And when it is strong enough, you order it. If the coupling are strong enough on the boundary, so you have the extraordinary or normal universality class. Yeah. In between, but not only for the Ising, but also for this ON models, the special universality class is actually when the defect is transparent, so it's perfectly translational invariant.
So in practice, you say that this picture is completely equivalent. For all practical purposes, it's equivalent to having a boundary, as opposed to just.
Yes, except that okay, the numbers are different for the extraordinary log phase, and that the special universality class is nothing new. It's equal to the bulk one. Okay. Yes, but yes, it's correct. It's equivalent.
Sorry, in general, it doesn't have to be equivalent, right?
No, I don't think so. But in this case, at least, yes, because you see, if you flow to a phase where this coupling here on the boundary, they becomes very small, you basically disconnect, and you have the ordinary. That's one case. Stronger one, then yeah, maybe depends on the model.
Why is it different at large n?
You will see there is a different formula. So basically, if you want intuitively, the extraordinary log phase is the consequence of having a bulk next to the surface which is gapless and induces more correlation. And for the defect, we have two of them, right and left. So they are stronger to trying to keep order the phase.
In the Ising model, can it happen that the left part of the world orders in one phase and the right part in the other?
Mm. To have one left, for example, in the ordinary, you will need to disconnect the phases.
Yeah, if you could disconnect them, it's obviously possible.
Yeah, and then I can imagine that you can maybe with a more generalized Hamiltonian. Maybe you have two planes to consider, and you study also the plane, the coupling of these two planes too. then maybe you can also realize the special against the ordinary, because then disconnect and the other one can have the special. All right, so what is the extraordinary log phase? So I already said that it's a almost ordered, but not quite ordered phase, where the two-point function decays is extremely slow with the logarithm. And the theory says that this exponent q, or equivalent this parameter alpha that enters in the RG flow, speak in a moment, is determined by some universal amplitude of yet another universality class, the so-called normal universality class. Another key feature that we'll talk about later is that you have a specific logarithmic behavior found in the extraordinary log phase. So detecting this two-point function would be hard, or if you want, numerical would be hard to distinguish with maybe some slow power law or so. But there are other key signatures which are much more stable for numerical simulation. So, right, so let's come to the first point. So, what's the normal universality class, and why it's connected to the extraordinary log phase? So, it's called normal. Why? I think I trace back to some paper of Fisher that was talking about the various transition in the Ising universality class. It says that the so-called extraordinary surface transition, which, however, in the laboratory is more normal than the ordinary transition. And why is it more normal? Because the typical laboratory physics to implement the Ising universality class, that they had in mind the Ising universality class, is a fluid, a binary liquid mixture, where you mix two species, and under certain condition, the demixing transition, which is shown here, that's an experimental picture in modified colors, it's an Ising transition. And the order parameter is one, is the deviation, if you want, or it's a concentration of one of the two species of the mixture. And now, it turns out that when you expose a fluid to any surface, could be a substrate, could be even a colloidal particle, depending on the chemical treatment of the surface, the fluid, the involved surface may prefer one of the components of the mixture. And you can model them by a surface or a boundary field. Now, including a boundary field defines what we call really the normal universality class. So for the Ising case, if you order the surface, when you put in a standard field, of course, you immediately order the surface. In the Ising case, the extraordinary one, so the one that you get by a spontaneous symmetry breaking, or by ordering the surface in a standard field, one can see quite rigorously that they have to be equivalent. So that's why also, and that's maybe a comment, if you look at much of the older literature, they use the word extraordinary and log as an interplay, as a synonym, because they had in mind the Ising case, or maybe the ON, but close to 4 dimension, not to 3. In reality, for the ON case, the things are a bit more different, because for the ON case, n larger than 1, first of all, you break the symmetry to a subgroup, which is still non-trivial, ON minus 1, so you want to distinguish modes on the surface which are orthogonal or parallel longitudinal to the standard field. They correspond to different boundary fields with distinctive different critical exponents. They are related to some protected operator on the boundary. You can see here, these are really real Monte Carlo data. If you look at the correlation which are transverse or longitudinal to the external field, no, these are longitudinal, these are transverse, they decay with a different distinctive power law, and these numbers are believed to be exact. Knowing that the normal universality class is connected from the theory to the extraordinary log phase, that we were motivated to study the boundary critical behavior and the boundary operator product expansion of the normal universality class. And to do that, we set up a Monte Carlo simulation of a model which is critical and represents the ON universality class. And my favorite model is not the classical hard spin model, but the 5 to the 4 theory. Why? Because in the 5 to the 4 model, you can tune the strength of the parameter to get rid of the leading irrelevant scalar on the bulk. This has been studied a lot. There's a long history in critical phenomena of this improved model. That's what they are called. And fortunately, we know a lot about this model. We know where the improvement parameter is. It's not always guaranteed that it exists, but at least for n equal 2, 3, 4 exists. And we know also very precisely the location of the critical point. So then we have the bulk physics is very well under control. There are basically very, very weak scaling correction. And then we can put this model on with boundaries and study what happens near to the boundary by including this time an external field, and realizes immediately the normal universality class. And of course you have to distinguish now we have broken the surface, you have to distinguish the two directions of the fields. Now there is a series of interesting boundary operator product expansion coefficient that we were interested, also motivated by the advancements on the extraordinary log phase. How do you get them? The first thing is that you should, out of the lattice model, find the connection to the underlying CFT fields. In the bulk, you have a ON vector, and a proxy for it is, of course, the lattice observed, the lattice of the parameter, which in general will be proportional to the underlying CFT fields, plus maybe some other correction coming from descendants or other operators with the same symmetry. On the surface, instead, at the normal universality class, you have two leading operators, a scalar one, which is the displacement operator and has a dimension 3. That's why the longitudinal correlation decays with an exponent 6. And the one which is orthogonal to the external field, the component orthogonal to the external field, which is again coupled to a protected operator, is called the tilt operator, and has a dimension 2. That's why the correlation orthogonal to the external field, they decay with an exponent 4. So now that you have first identified what are the candidates of the lattice observables, you have to know what's the normalization here. And to fit the normalization, you compute a two-point function. So you assume that the CFT fields are normalized as usual with a prefactor 1 in front of the power law. And so by comparing this and the expected expansion with a suitable fits, you are able to get the normalization. Now this is doable for this lattice field, for the tilt one. For the displacement is hard. It's hard because it decays very fast, but we'll tell a bit more later on. Then next to the normal universality class, you have a boundary to bulk operator product expansion, which you have to distinguish the two-channel parallel and orthogonal to the external field because you have broken the symmetry on the boundary. And so accordingly, the longitudinal part expands into all the scalars on the surface, so the identity, and the next one is the displacement, whereas the vector part explains in all the vector on the surface, and the lowest lying one we think is the tilt operator. Now, with that in mind, these two coefficients are the universal OPE coefficient that we are interested in to extract. All right, so how do you extract them? Well, from the boundary OPE, you can take the expectation values of this equation. The first one, you can take the expectation value. The second one, if you take the expectation value, you get 0, so you have to compute a two-point function, bulk and boundary. And the amplitude of the bulk boundary or the one-point function of the other parameter directly has in front, apart from some numerical factor, you directly have in front the desired OPE coefficient. Then you plug in the dictionary between the lattice and the CFT. You also have to include all the possible scaling correction that comes from a finite size, the existence of an irrelevant displacement on the boundary. You come out with an answer like this one, which seems so horribly complicated, but the key point is that the exponents here, the 3 and this delta phi, they are known. We plugged in from an outside, and that makes the problem doable, because then you basically are fitting just the amplitude of this scaling correction.
So what's Z naught?
All right, so Z naught is the accounts for the leading correction Z to minus 1 that comes from an irrelevant operator on the surface, which is the displacement one. Now, if you expand this, it will always be Z to minus 1 for Z large Z.
So you're saying that if there is some displacement, it's just going to shift Z by some number that you don't know.
Exactly. Exactly so. You can also show this.
But Z naught can depend on L, or you can...
No, so the leading correction is the one that you get by imagine. So you have two corrections, one coming from finite size L, and the other one coming from the relevant operators. The one from the relevant operators you get by imagine L going to infinity, and then this Z0 is a model-dependent constant. Right. And yes, and that's also an interesting point, because grouping this way means that the Z0 is the same for all observable. That's the non-trivial part of these corrections. And if you also notice to this ansatz, you see also why I was interested to get an improved model, because the Z0 gives a correction Z to minus 1 But then you could have also the bulk that gives a correction 0.8, too much close to 1. So it would be difficult to disentangle. One can live with that, but it would be difficult to disentangle or would give you less precise result. So that's why with the improved model, we are on a better side to get precise numbers. All right, so there was also some conformal bootstrap work going on at the same time. Unfortunately, the positive conformal bootstrap is not able to single out a small island as we would like to have. This is showing for n equal 2 and 3. You see that this is the island of allowed values of the two boundary OPE, and the Monte Carlo it's a very small number here. There is also the truncated conformal bootstrap, which does a reasonably good job. However, it's within the uncertainties is outside the Monte Carlo data. All right, so then, okay, by repeating the work for n equal 2 and 3, we get some estimates for the two OPE coefficient, and what we do with that. So the theory is that these two coefficients, the normal universality class, are related to the alpha parameter described in the extraordinary log. And you have two formulas for a case of a surface or for a case of a plane defect. And to answer your comment before, you see that the plane defect basically has twice the contribution coming from the bulk. That's the contribution coming from the bulk. And that's why it stabilizes the extraordinary log phase. As long as alpha is positive, then we have the extraordinary log phase. And based on the number we have extracted from a sigma and bt, we can also compute alpha according to these formulas. And the only number I can compare with, so there are these islands, but they're not particularly pinning down the value. I can compare with truncated conformal bootstrap. You see that it does a reasonably good job, but it seems to systematically overshoot the value of alpha. All right, so where this alpha enters from, no? So the field theory description is that we can model the extraordinary log phase. So now I'm going back to the extraordinary log phase without a surface field, as a nonlinear sigma model coupled to a critical bulk. The question is how the coupling cost of the nonlinear sigma model flows under the RG. So it will be described by a beta function that close to the order phase g equals 0 can be expanded in powers, and the lowest part is g square terms. Now the alpha, this g square term is responsible for the decay of the two-point function as a power of a log with this relation between this RG parameter and this exponent q that comes from solving the equation for the two-point function. So I already said that this would be very hard numerically to see or to pin down this exponent just by looking at a two-point function, because basically it decays so slowly that you would have a hard time to distinguish an exponent. But there is another set of predictions that are rather much more stronger to see in the extraordinary log phase. You see, when you look at this parameter alpha, now I'm taking just the leading parameter beta, you basically have two contributions. The first one is the contribution that you would have just by having a nonlinear sigma model in 2D. The beta function is known, even the next term, I think, and it is known that for n larger than 2, it flows away because we never have an ordered phase for the Heisenberg model, for example, in 2D. This is a negative part that flows away from g equals 0. But then it picks up a contribution coming from the bulk that may reverse the sign, reversing the RG flow and flowing now back to g equals 0. And you can see this by looking, for example, at the stiffness. The stiffness, basically, you can compute the lowest order in perturbation theory, basically picks up the g of the nonlinear sigma model. And so now if the g flows under a RG beta function like this one, you will predict a logarithmic behavior where the prefactor depends on this alpha prefactor. Here I'm showing the stiffness when you pick up a 2D surface which is isolated, this for the Heisenberg model. And you see that the stiffness goes down. This is a semi-log scale up to, I think, maybe 300 or so, maybe 384, I think. You see that it goes down logarithmically. Now, when we attach this surface next to a critical bulk, there's a different normalization, but then you see the slope is changed. Now it has reversed. Now it's growing logarithmically in L. implying that this alpha has changed sign and the system goes back to the order phase, but logarithmically slow, so that you don't really have a true order.
Remind us what the definition of the spin stiffness is.
So it's the derivative of the free energy with respect to a twisting angle, the second derivative, computed at zero twisting angle. So it's the response of the system under a torsion in the spin space. You could also diagnose it, for example, to help to understand if the system is really ordered or not, by seeing if the stiffness goes to a constant or not. All right, so we do have a clearly prediction, also a qualitatively different behavior in the presence of extraordinary log phase. I call this kind of behavior a logarithmic violation of finite scaling. Why? Because usually at the standard critical point, Rg invariant quantities like the spin stiffness with a correct normalization in L, they go to a constant. Instead here they are exploding, they are divergent but logarithmically slow. And we have systematically studied this by looking at the stiffness for open and for plane defect. It's also called the Listley modulus in the context of this classical modus, if you see this in the literature. Another Rg invariant quantities which is very commonly used in critical phenomena is the ratio of the correlation length over L. That also picks up 1 over G, and you can also expect a growth in the log of L. This is an example for the open boundaries in the extraordinary log phase for n equal 2 and 3. For these two Rg invariants, you see that all of them in a semi-log scale clearly show a growth as a function of L. Maybe the xi over L seems to be for small lattices more scaling corrections, but overall it fits nicely a log behavior. And by the way, the fits of this log behavior gives a value of alpha which is very close to the one that we predict from the normal universality class, but I will come later to this point again. We also did the same job for a plane defector, this time also going to up to n equal 4. And again, you see clearly in the extraordinary log phase a log growth. And this is a very on a qualitative level, it's a clear prediction that you can see on the Monte Carlo data, much more than just looking at the two-point function that decays so slowly that, yes, it could be a power of log, but it's hard to see numerically. We can do more than that. You can actually directly determine the beta function, the expansion at least, the lowest order of the beta function, by using a method that was introduced by Lucia, Weiss, and Wolf. And the idea is the following. We know how to the lowest order in perturbation theory how the relation between the helicity modulus or the xi over L with respect to the coupling constant. And now we reverse this equation and take this seriously as a definition of a renormalized coupling constant. So this is a good definition of G with the right normalization. And the first coefficient of the beta function are also universal under the rescaling. So we can really promote this as a RG as effective renormalized coupling constant and follow the renormalization group flow of these quantities. Now, in the method introduced by Lucia, Weiss, and Wolf, one introduced effectively what's called a step scaling function, where you look at what happens when you increase the lattice size from L to, for example, 2L, or one of these RG invariants, basically. And you study this not as a function of L as before, but as a function of G itself. So basically, you are replacing the derivative that you have in the flow, the renormalization group flow, by a finite increment. And now, if you start from a beta function which has this expansion here, this step scaling function that you can compute with Monte Carlo, it's just the same data but analyzed differently, has also a similar Taylor expansion where the coefficients are directly related to the coefficient of beta function. And so the idea is, the left-hand side we got from Monte Carlo, G, this sigma versus G. The right-hand side we can fit. There is a leading linear term that we can drop away immediately, that's trivial. And the rest gives us an access to the coefficient of the beta function. So that's the kind of plots you find. I've already subtracted the leading term. We can use different definition for G. And here I'm plotting the sigma as obtained from the Monte Carlo data. I'm showing you the black line is the line that you would expect, so the sigma function that you would expect by truncating the beta function to the first to the first g square. So we'll get this term here and this term here, but not this one. And you see, especially from the stiffness data, which seems to be much cleaner, well, for n equal 2, they more or less lie on the same curve. Maybe for a larger value of g, they start to have a bit of a deviation from this black curve. Here I'm using the data of alpha as we know from the normal universality class, but overall it's very close, and that's also a very clear check, also if you want quantitative check, that the alpha that we got from normal universality class is the correct alpha entering the RG flow of the extraordinary log phase. Things are instead the deviation from the black curve, from the lowest order, is much more evident when you go to n equals 3, where you see that the points very deep in the extraordinary log phase, they align on the black curve, but if you go a bit away, there's clearly a systematic deviation. This systematic deviation comes from the next term in the sigma, which in turn is related to the next term, the subleading term in the beta function. So we have fit then the right-hand side here, and the fits to the right-hand side is the one that I'm showing here under this gray range. So the thickness of this reflects really the uncertainty on the next to leading term, fitted term, which, for example, in the n equal 2 case turns out to be small. That's why you have a very weak correction. The n equal 3 instead it starts to be larger. The data for XRL seems to be more affected by scaling correction. You see anyway that, they don't really all fall into a curve, but if you take just the largest lattices, then they fall under the black curve. And same also goes for n equal 3. So it seems that the XRL is maybe more sensible to the scaling correction than the stiffness.
Can I ask a question about that? So this method of Lucia et al., it allows you to cover effectively much larger range of length scales, which you would have done if you tried to fit everything into one huge lattice. Right?
Yes.
Because here you are covering, you are not able to cover this running of G in one big lattice, but because you put together everything.
You mean that
you're saving a lot of computational power by using this method, right?
Yeah, because I'm showing that they all lie on the same curve, and so I can just increase the computation. That's what you're saying. Yeah. So instead of I pick this one and I insist in increasing L, but eventually I stop here when L is. That's true. That's true. There's also another thing is that. This term here, maybe say more. If you just analyze the data, say stiffness versus L, the subleading term will give you a correction which is like log L. That's why you will never be able. At some point, you increase the lattice size, but you get stuck to. You will be basically for say I get this value of the orange point to arrive here. I will even exceedingly large lattice sizes, and also I see some correction coming from the behavior. If I just study some quantity versus log L, I will see some correction because the effect of B in all cases is we found a negative value of B. Basically, it slows down a little bit the flow to G equals 0, and so you effectively see. Over some range of lattice size, you could effectively see in a value of alpha which is slightly biased to a slightly negative value. That's just an effective behavior. So if you were able to do any large L lattice size, you will eventually get the right alpha. But on a finest L, that this B term is giving you such a slowing correction that may be very hard to see, in particular if you are not very deep in the extraordinary log phase. A couple of things that we, as a byproduct of this, is that, well, first of all, if you have estimates of alpha and beta, it's tempting to find another zero of the beta function. This one, an unstable one. And what will be this zero function? Will be the special universality class. You can try with the number we have to see if, for n equal 2 and 3, this is the special universality class is perturbatively accessible with this number. Turns out that n equal 2 is too far away from the G equals 0, so when you plug in the numbers, the exponents you will get by just truncating here and finding the 0 are clearly different than the one of the Monte Carlo. For n equal 3, instead, you have maybe a deviation of 10–20%, so it's still reasonably accessible perturbatively. And the other thing is that what happens when alpha becomes negative? So when alpha becomes negative, and you don't know what's happening after this, all you can say is that the g equals 0 point is unstable, but you don't know what's happening after. So when b remains negative, then you can also say that basically that's the only, there are no other stable fixed point. If b were positive and this alpha becomes negative, you could find another stable fixed point, some interacting fixed point. In all cases we have b negative, and so that indicates that when the alpha becomes negative, so when the n is large enough, basically there are no other fixed point. That's at least that's the indication of the. So there are no some other interacting fixed point. At least that's the indication of the numerics.
Is there a theory for b? Like for A, alpha, you said, okay, it was a contribution from the sigma model plus some CFT correction. And for B, can you also split it into sigma model plus CFT correction?
I don't know. I suppose that maybe some higher order correlations on the normal universality class maybe can get to it, but I don't know. That's an excellent question for the field theory guys here. Maybe can get something that can be measured.
In your plots of sigma, you chose some value of s?
2.
2.
Right. Okay, so maybe I'll then be very quick on a short intermezzo section on the quantum dimerized quantum submodel, because that's where I personally started to go back to this classical fields of boundary critical phenomena. There was some surprise a few years ago, and Longzhang and Fa Wang, they studied the dimerized quantum spin model, a simple spin 1/2 model with this Hamiltonian, this interesting lattice, which undergoes a series of phase transition in the bulk and the ground state. And all these transitions between some dimerized phase and the nil phase, they are all in the O3 universality class, just by, if you want, universality arguments and quantum to classical mapping. The surprise came from what happened to the boundaries when you put this model with 3 edges and you measure the critical exponents on the boundary. And while the new exponent, in all cases, matches the one that we now know with a very high accuracy by conformal bootstrap and also Monte Carlo, the one on the surface at the time, depending on the transition, was even 2 distinctly different exponents. And at the time, so one, only the ordinary universality class was known, and one of the exponents clearly was very close to the ordinary one, but the other one even have not the same sign. So they were falling slower than the power 1, the 2-point function. This has attracted a lot of studies. This is just a small selection maybe of the things that people have done. We have also contributed, and we have studied a series of dimerized quantum models. There's been a series of hypotheses why this is happening. We have studied a series of dimerized quantum models with different geometries, different cuts, depending on what you put the boundaries. We identified an empirical criterion where at least this new exponent comes out. So if you start from the gapped phase, the dimerized phase, you can always identify what we call dangling and non-dangling spins. So the spins which were non-dangling one are the ones which are coupled, which are with the strong bonds to some other spins deeper in the bulk, and the dangling one are the ones which are decoupled. This distinction, of course, makes sense, strictly speaking, only in the dimerized phase. When the bulk is skewed to a critical point, then you can't separate the surface from the rest anymore. But if coming from a dimerized phase, you go to the critical point, the non-dangling spin are the one which shows the ordinary universality class, and the dangling one are the one which shows this new, at the time unknown exponent, but it's not fully clear yet. Similar results were also been done by Wen and Gu and co-workers. If you now, that was for me a motivation also to go back to study the classical O3 model, because we were always comparing with the O3 model, but maybe it was not fully understood. And it turns out that there is a special transition with a standard exponent. One thing that comes when you look at the numbers is that the...
Can you say, what does it mean by special? Can you be the standard exponent? What does it mean, standard? You said this already several times, but I should have asked before. So.
I mean that there is just one relevant operator with positive dimension. There's no marginal operators or some more fancy transition. It's just the standard transition will have irrelevant operators, and that's it. So what I call it this way because the previous Monte Carlo work was suggesting that maybe there is a sort of KT-like transition where the RG invariants are flattening with an unclear crossings. That was the origin. The number you get in the dangling spins are very close to the exponent of the special transition. So I think maybe Cenk and co-workers were first pointed out that maybe it's because these models, when you are in the dangling regime, they are accidentally close to the special transition. They maps to this point around here. When I say accidentally, it's because the special transition needs fine-tuning. So how comes you get there? Maybe one ingredient is the fact that the leaning exponent here is very small. So there is a relevant perturbation, but it's very close to be irrelevant. And so that means there is a slow crossover here in this region, and maybe even if you don't map exactly at the special point, you will see still Fana's scaling dominated by the special point because of this comparatively large crossover region. That's at least is one explanation. It's admittedly it's not a complete one because you would like to understand exactly why this is mapping there and why there seems to be that many different models gives you a exponent close to the special one. So there must be a reason why you always, in some cases, you flow, you end up very close to here. It's not unfortunately the end of the story, so this is an unfinished story because to understand this, you would ideally get a dimerized quantum spin model and study the surface transition, the edge transition. That's what Wennan and collaborator did with some dimerized model, but they found the special transition is completely different to an ordered phase. The special transition seems to have completely different exponent, and it also goes to another kind of phase, an ordered phase. So that does not fit this picture. It also seems to contradict some field theory results by Gabriel and Zhang that saying that you should not be able to break a continuous symmetry, even if it is at the boundary, 2D boundary of a 3D 2+1 dimensional critical bulk. So the
dimerized model, the middle one, the QMC, are you saying that the quantum model is different from the classical model of the special transition?
Apparently, yes. The numbers are very different, apparently. That's what they fit. So there's
no dangling spins or anything there?
No, I mean, what it means dangling. They are dangling when it becomes critical, you can't really know, you can't really define rigorously what is dangling. Dangling is a notion that we took empirically from the phase when it's gapped, the bulk is gapped, and then we tune the bulk to the critical point. Yeah. So, and we think we end up in the extra analog, close to the special point. Yeah. There they don't do this. They really take the quantum dimerized model just to increase the strength of the interaction in the boundary.
Yeah. So the dimerized model has no.
No, it's not really. Yes, so it's not anymore in this picture, but it seems to be very different. So, but also the order is also unclear.
Is relativity preserved at the boundary?
Sorry, is
the fact that the boundary is described by some boundaries of T.
That's the hope. At least that's the idea. I should say that one ingredient that makes maybe things complicated is that there is a flow of the surface velocities, and this is logarithmic one. So maybe that's also a possible trouble in doing the Fana's scaling.
Yeah. So I don't understand the relation of this second story to the previous one. The previous one, everything was beautifully in agreement, including n equals 3. Now here again, n equals equal to 3. So what is? So here you see some contradictions. There you didn't see any contradictions. So
before I had just a classical model. Now I'm doing the quantum one, which I think under the quantum to classical should be the same. And we don't understand. But first of all, one should like to understand where this quantum model exactly maps to in this phase diagram. We think that for some, we don't have a full control, but it would be interesting to understand where exactly, why, for example, for many models, U seems to be close to this one. But then again, there's another model that seems to not fit this idea. So,
of course, possible explanation could be that, okay, I mean, certainly there are other boundary universality classes for the Heisenberg model. I mean, these ones that ordinary special externally, this is just one family of boundary conditions that or Heisenberg CFT has, but it probably has infinitely many other boundary conditions.
And this dimerized model are accessing them.
Yeah. And which you did not access in the statistical physics, but here you're lucky that you can access them.
Maybe.
Yeah.
As I said, it's an unfinished story, so I think that's also something that one should understand, try to understand more.
Okay.
And people try to interpret it by, let's say, considering a 1 + 1 DCFT on the boundary and then interact with the bulk. That presumably can give you many different types of boundary universalities.
I think so. Maybe Max did some work in this direction, but you may have some on the boundary. You could have a theta term. That escapes the classical thing. However, people have done this dimerized spin for spin 1/2 as for spin 1, and you get similar numbers. So the theta term maybe is not that relevant there, at least for this class of dangling on dangling models. So, yeah. As I said, this is an unfinished, still interesting story. And the remaining part of the talk, I'll maybe talk to you a bit more, maybe technical, but a study that we've done also the simplest possible. Now here there's no ambiguities. The model is very well defined. It's the Ising model with a surface studied a lot. We know at least known universality classes on the boundary are this ordinary, the special, this extraordinary, which is equivalent to the normal ordered phase. You have to symmetry, Z2 is a symmetry of the model, it's symmetric boundaries or symmetry broken boundaries. The exponents are known, the phase diagram is known. What was not that well known are the boundary OPE. And there's a series of boundary OPE that you can study by fusing, for example, the order parameter phi next to the boundary. And if you have a Z2 symmetric boundaries, then it couples to the boundary surface. If you have a broken symmetry on the boundary like the normal one, then you also have the identity coming from the expansion of the bulk field next to the surface, and the next operator will be the displacement one. You also can also do take the even operator, the energy operator next to the surface, then you again expand for all possible universality classes. Then you have the identity, and then the next leading operator, which depends on the universality class, what it is, this O. From the in the Z2 symmetric universality class, you can also take the bulk surface product, and this relates directly to this coefficient here. Plus, of course, there are also some correction that defines yet another boundary OPE coefficient. And we have explored all of them, all of this, for all these three universality classes by Monte Carlo simulations. The idea is that we take again an improved model. This time is the Bloom-Capell model instead of a standardizing one, because again, for the 3D Bloom-Capell model, you can tune the coefficient in front of a square in order to eliminate the leading irrelevant even operator in the bulk. And again, these models have been studied a lot in the past, and we know to a very high precision where this special point is, what is the critical point. So again, we have the best model to realize the Ising universality class. Again, we have to connect the lattice to the field theory underlying and to identify what are the lattice observable that couples to the two low-lying fields in the theory, the even and the odd ones. The field, of course, is coupled to the order parameter as the spins on the lattice. For the even parameter, you can actually think of two possibilities: the local energy, so like a sum of a nearest neighbor interaction, that you can also do for an Ising model. For the Bloom-Capell model, you can also take S square, because S square is not necessarily 1 for the Bloom-Capell model. We have tried both of them. They give the results in full agreement with the two. The energy seems to be a bit more precise, as a side remark. you again, you find the normalization constant by fitting the two-point function of all these observables. And this allows you to get this normalization constant. And also as a byproduct, you also get, by studying the subleading term, the operator product expansion of the Ising theory, which are in agreement with very precise conformal bootstrap results. They are, of course, less precise, but they are in agreement. So that's nice, and we see that things are well under control for the bulk. For the surface, again, a similar job. We have to generalize the Hamiltonian to include a surface term with a different interaction, and possibly also a surface field. Then you have a bigger phase diagram, and the good thing is that the phase diagram has been already mapped for this Bloom-Capell model. For critically improved Bloom-Capell model, we know where is the special universality class, for example. Again, you can identify lattice observable on the boundary. Of course, the boundary spin is directly equivalent to connected to the boundary field. For the Z2 symmetric operators on the boundary, you can again study the local energy or the local S-square operator, and this connects directly coupled to the relevant operator, which I call epsilon here, the relevant operator at the special universality class. As I said in a moment, we use this expansion only for the special universality class, because for the ordinary universality class or for the normal universality class, this even operator will couple to the low-lying even operator of the ordinary, or just a low-lying operator in the broken or normal, which is the displacement operator. This has a dimension 3, and it's hard to fit then very well the normalization, because you are fighting against a two-point function that decays like R to 6. And so it decays very quickly. At shorter distance, you still see a non-zero fluctuations, but short distance is non-universal. You would like to go to larger distance, but then it decays too quickly to get a precise value of the normalization. So in this case, we have used a different trick that I will take to you later. All right, so once you have the dictionary between CFT and lattice, then you can try to exploit all the possible correlations, one and two-point function, to extract all the boundary OPE that I was showing here. So I will not go through all the list of showing all the observables, because otherwise we never finished and we'll bore you to death. Maybe I'll take a couple of examples because to see how the machine works. Let's take, for example, the special universality class. So for the special universality class, the exponents are known. We have also improved one of the exponents, the scaling dimension of the fields on the boundary. Let's say you take, for example, the one-point function of the energy, which couples to the even operator of the bulk. By studying finite scaling and using the operator product expansion, you see that this one-point function has to decay to a constant, non-universal constant, simply the infinite volume the thermodynamic behavior of the energy. And the decay, subleading decay, has a power law which picks up the energy dimension in the bulk, and some subleading term which picks up the leading even operator on the boundary, plus some subleading scaling correction. These amplitudes, this one here and this one here, are directly related to the OPE coefficient. One is just a normalization times the one OPE, the one with the identity. The other one contains one OPE coefficient times the finite size amplitude of the operator epsilon, in this case for the surface universality class. So the finite size amplitude of the relevant even operator at the special universality class. Now, from fits to the bulk, we get well, the exponents are known. If it's on the bulk, we get the 0. So we plug in from outside, and we get the normalization. So then, by fitting this amplitude, then you get a epsilon. By doing fits of surface observables that couples to the epsilon operator, you can also extract this finite size amplitude, u epsilon, and then by using this formula, you extract the desired OPE coefficient. Now, when you do this kind of job, so you have to ask yourself, when is this scaling answer valid? So it will be valid not at short distance. So you have to systematically throw away the short distance in order to throw away the non-universal physics. You have finite size correction. This one is the first, the leading finite size correction, but of course there will be other terms. And here the final size corrections are given by the scale z over L. Z is the distance from the surface. So you have to also systematically discard the data which where for z over L is larger than some threshold. You have to do this systematically in order to see how stable the results are and how good the fits are. And last but not least, for all these two parameters, you have also to systematically increase the smallest lattice size taken into account, because smaller lattice could have some extra corrections. So what are the criteria? First of all, the stability of the results, and second, of course, the goodness of the, as usual, the goodness of the fit of the chi-square. At this level of precision, there is also some statistical covariance that one have in the points, because basically you're fitting the correlation of data that comes from the same simulation. So there is, at this level of precision, still a bit relevant input in the uncertainty due to the covariance. And all the inputs parameter we fit from outside will also vary them between 1 error bars to be sure that what's the impact on this final result. That's one example. The other example I have in mind, because
yeah, on the previous slide. So this value for the special universality class 0.35.
Yeah.
That's for the lowest relevant operator.
Yes.
Is
old operator. Old operator. Yes.
Is it in tension with bootstrap? I thought that there is always like 0.42.
No, not that I know. That's a good question. Maybe somebody knows. Not that I know. Not from truncated conformal bootstrap, for example. There is for the ordinary. There is a truncated conformal bootstrap calculation. For the special, I don't think they have a range of
I thought the estimate was like 0.42 in the bootstrap.
Okay, maybe we can show you later the reference.
Another example, that just to show that there is a slightly different procedure. Suppose I take the normal universality class and then I take the 1-point function of the order parameter. Okay, so similar argument gives you the scaling ansatz. Again, an amplitude that depends on the normalization of the field times my universal OPE of the field to the identity. The subleading term. The subleading term contains the next operator after the identity, which for the normal universality class, but same thing happens for the ordinary, is the displacement operator. So you find that this amplitude here is proportional to the desired OPE coefficient times the amplitude of the displacement operator. Now, previously, for we had the amplitude of the we had the amplitude of the amplitude of the energy operator at the special universality class, and we determine this amplitude by fitting again the lattice observable on the boundary. If you do this with the displacement, it's much harder, because the displacement necessarily you need to normalize the lattice observable, and by computing the 2-point function, this is the case very quickly, so in exponent 6. So there's another way out to get UD instead of using the correlation, and the idea is that we connect the displacement to the energy momentum tensor. So this is has an expansion like this. So basically, there's a normalization factor relating the ZZ component of the momentum energy tensor with the displacement operator. And the expectation value of the tensor is basically what is called in the fields of critical phenomena as the critical Casimir amplitude. So this is a quantity that we can compute. There are some known procedure algorithm, basically a Monte Carlo plus an integration. So we can get access to this one. So now we have introduced a new constant, however, in the game. So we can substitute the UD with the amplitude of the tensor TZZ at the price of we have introduced a new known constant CD. You can close a set of equations by using the identity due to Cardi that relates these two boundary OPE coefficient with the normalization of the tensor ZZ. So Cardi wrote in a slightly different manner, but here I'm using this normalization for the displacement. And then using this identity and the relation between the TZZ and displacement inside this equation here, you get another equation relating the CD norm with the fitted amplitude. Then you are able to close the system of equation by fitting, you know I5 from fitting the amplitude in front. You get from this equation the value of CD, from this equation actually, using the Casimir amplitude that we can compute. And then you plug inside here, you get a ratio, and then eventually the desired OP coefficient. As a bonus, you also get another universal quantity, which is the normalization CD.
We're out of time, by the way.
We're out of time. Okay, so then I will just show you the results. So there's this is the final set of results. For half of them, I'm not aware of other calculations. So if you know something else, please approach me. We can also compare this with a truncated conformal bootstrap, which in many cases gives a reasonably good answer, but of course introduces some systematic error. I'm also computing with a very recent work on the fuzzy sphere, this here, which also calculated the various OP coefficient. You see that in some cases there is some, especially for the CD, there seems to be a more systematic error coming here. There's also some other works that we have improved by reanalyzing older data. Before I go on, let me say that there's also experiments going on that you can do on this. A real experiment, not a numeric experiment. People have studied a lot in the past the critical absorption experiment. So you basically you take a critical liquid, you expose the substrate, and you measure the densities or all the parameter in our language. This must have this scaling behavior as a presence of a finite correlation line. So now I'm not exactly at the critical point, but I'm close to it. And this scaling function has some known limiting behavior. And when the xi is infinity, you have this behavior. Now this is exactly what you find as the profile that you find here. So it decays with some exponent when the system is critical. So there has been quite a lot of experiments. Floeter and Dietrich a while ago, they took all various experiments available at the time and tried to compute this universal constant here, and they found a lot of scattered value, unfortunately. A more recent value, I think, is this one. I found this one of Carpenter, Lowe, and Smith, still, however, 20 years ago. This amplitude is directly connected to the OP coefficient that gives the field next to the identity order. There is a different normalization, however, so that one has to find the correct factor. It's a universal, of course, quantity, so it's multiplicative with a universality quantity. So if you now translate this value in our notation, you find this value of alpha. That's close. However, maybe there is a bit of a tension between the final Monte Carlo we have and the true experiment. So it would be interesting if one can do more experiments on this. With it, I like to acknowledge the collaboration with my collaborators. So Abi and Max on the various topics of the ON and extraordinary log universality class, Lucas and Stefan for this work on the quantum dimerized spin model, and also Stefan and Dorian, who was a student in Aachen, for this last part of the talk on the Ising universality class, and of course you for your attention.
Questions?
For the cases where you have a mismatch with the quantum, you can take the same lattice structure and simulate some classical models. You do that? So you can define the dangling spins also for a classical system, and do the simulation for a classical system and see if you get the same thing or not. Has that been done?
It's not been done, as far as I know. If you dimerize the interaction, of course, you will, as a function of dimerization, you will have a line of transitions. So for every strength of the dimerization, we will have another special fixed point. It's not been done, as far as I know. Maybe in this way you could understand if there are more corrections that becomes more subtle to see. But it might be also that there is an effect of quantum, the fact that the spin is really quantum, that you have, for example, a flow over the surface.
S equals a half and S equals 1, you see no difference. So
that's exactly what we are. We don't really fully understand why this other model of Winan is giving a different result.
And one question,
Yeah.
you talked about using phi-4 theory with some improvement in Bloom-Capell, also for improvement later
Yeah.
on. Why do you choose one versus the other for different situations?
So you could also, for the Ising case, you could also take the phi to the 4 theory. That's also there's a known value of the improvement. It's easier to simulate the Bloom-Capell because it's discrete. So the states are much less memory, and they are also numerically stable. In the other case, you have to deal with float numbers, so a few of the algorithms might have to be checked for the numerical stability. In the Bloom-Capell model, everything is discrete. It's also much faster, of course, to simulate by this.
And
Yeah.
Bloom-Capell in the first case wouldn't work because, or why didn't you use it in the first?
Sorry, Bloom-Capell?
Yeah. Oh, or was it just because, did you do QMC? I guess Bloom-Capell for the first case where you...
For the ON model, you mean?
Oh, for the...
No, but your original model, you need a vector, a vector.
But you would introduce some dilution and tune dilution, and maybe this is also going to tune.
Yes, definitely. I think people maybe have already tried. The phi to the 4 is the most studied one, so that's where we have the state of art.
Okay, I think this is encouraging some discussions, but maybe we could...
Thank you. A short comment. Yeah, the phi-4 theory has a terrific cluster algorithm. Hashim just uses it. It's
That's right.
just as efficient as the Ising model.
That's right, that's right.
So I don't think there's any choice from the point of view of the algorithm.